So, good morning everyone. I'm Rodrigo and I'm here to talk to you about robot self-calibration from touch events. A little bit about my previous background. I studied in Technical Lisbon, where I took the master's dissertation on the topic of adaptation of a robot body schema based on touch events. Currently I'm taking a PhD here at Queen Mary under the supervision of lecturer Lorenzo Iamone, which you have already met, on the topic of sleep detection with 3-axis Hall effect based soft skin sensor. It's a slightly different topic than what I've researched previously. What's up now? Okay, so our history begins when we were trying to find a way of calibrating a robot, taking some time, trying to find a way of calibrating in an intelligent manner a robot while it's executing its normal tasks. So we decided to take inspiration on the human self-development of their motor skills, our motor skills. So for those of you who don't know, there are several papers supporting the fact that humans develop during early ages of their infancy. They develop a neural representation of their own body schema in order to operate in their environment. Robots, on the other hand, are typically assigned with a static model of themselves, which are prone to time-degrading factors such as friction, worn joints, so on, which leads to the need to calibrate this over time. So, we set out to devise a real-time calibration strategy involving contacts on known surfaces on the robot workspace. In order to achieve this, we want to rely on tactical and proprioception sensors, and we set out to implement the strategy on an iCub robot simulator. And the reason why we choose the iCub robot is because its proprioception is given to us by what are called relative encoders, which typically, very often gives us values with biases. So we thought that an interesting way of improving the robot accuracy would be to estimate these biases. That's why we define a state, which we aim to estimate throughout the robot's life cycle, as this array, which we are shown here with the different biases along the robot chain, kinematic chain, which could be, for example, his arm, it's right or left arm. And the way we formulate this problem is as an adaptive parameter estimation, specifically the extended Kalman Filter setting, which basically, in a way, tries to make some sense of some contact constraints that are obtained from contacts on surfaces available to the robot workspace. The way we use this Kalman filter is by incorporating what are called the dynamic and the observation models. Okay. The dynamic and the observation models of our problem. Here the dynamic just defines how the state behaves temporally, and the observation is basically an error scalar which gives us the error, the distance between the predicted end effector position and the surface that it's supposedly contacting. So I won't go too much into detail here, but we try to implement 3 different strategies of incorporating new data into the extended Kalman filter, either varying the number of observations coupled together before doing a prediction step, trying to evaluate the entropy evaluation of each new data and discarding those which we believe won't give us relevant new information, and provide some sort of anti-wind-up control of the estimation process. So we experiment our strategy in an iCub simulated environment. Here we see that the robot is trying to reach for 3 different surfaces on its workspace. On the right you see an oversimplified behavior of the iCub left arm, which is basically randomly searching until it contacts the surface that is aiming for. As part of our experiment, we try to estimate some artificial introduced offsets along the left arm of the robot, of the iCub robot, and as a result we find out that we are able to achieve, to reduce the model inaccuracies by up to 80% using both anti-wind-up control and entropy evaluation. And also we found out that this strategy is robust both to different biases present in the chain, as well as offsets that are slowly time varying along the robot's life cycle. So thank you. If you have any questions.
Okay, thank you very much.